In my previous video, I explained why there is no naive approach to talking about boundary of Gromov hyperbolic fillings. So how do we remedy this? And this is where all these examples I have been bothering you with come in handy. Let's talk about 0 to infinity. We wish still to say that maybe my original space lives here at the end of this ray. Maybe it is down here waiting to be converged to. But how do we make sense of this? So let's look at the infinite ray. Topologically, you can still identify it. You can take one point compactification of your space and infinity pops out. But as a metric space, it doesn't make sense, because how do you define distance of infinity to, say, 0? You can't take it infinity. Infinity wouldn't make it a metric space. So we want to do the compactification, but also in a metric way so that this becomes a finite value. So how can we make distance to infinity a finite value? We have to scale down, in other words, uniformize, the technical word is, the distance. So instead of having all these segments being equal length, let's make them shorter as we go further ahead. So, and then when you add all these distances to kind of make sense of distance to infinity, we want this to be finite. But what are some convenient summations that converge? Well, geometric sums, right? And also they are geometric. We love them. So let's say this one has just distance 1 as before, but now this has a shorter distance lambda. And then this has lambda to the 2, lambda to the 3, and so on, where lambda is some number strictly less than 1. And then we will see that the distance will be finite, which is actually 1 over 1 minus lambda, finite. So to make it continuous, we go with the following. dxy becomes infimum of integral over gamma of lambda to the power distance of gamma s to 0 ds, where gamma is a rectifiable path in usual distance that joins x and y. So this is exactly doing what we explained. It weighs down. So if you are somewhere here, the distance, if this part of the path, distances to the 0 are comparable to 3. They're between 3 and 4. So here this weight is lambda to 3, basically. So in this part from 4 to 5, it's between lambda to the 4 and lambda to the 5, and so on. And that's why this becomes finite, even if you integrate it throughout this whole infinite ray. This converges to 1 over 1 minus lambda if n goes to infinity. So that space, now here was x, let's say g. This was g with the original Euclidean distance. And if we now draw g with the new distance and think of it again embedded in R2, it will be here. So this will be 1 over 1 minus lambda back here. So g with the new distance, let's call it lambda, d lambda, will look like this. And this point is not in the space. This is exactly the infinity. And you have 1, and then 2 is actually shorter, 3, 4, and so on. So this exactly did what we wanted. It shrinks the space and brings infinity back to a finite distance. And therefore, now we see that metric completion of G minus G is a singleton. So this space is no longer complete. So uniform change of distances may make a complete space a non-complete space, as we see here. And therefore, this point here is outside my space G. Therefore, we can call this the boundary of G. Let's put this lambda here. So the boundary in the original distance was empty set, but now in this new uniformized distance, the boundary consists of a single point. You can imagine very easily that if you do a similar thing here, each one of these rays has some point waiting at the end. And for that, for example, you can say all the edges at level 1 are scaled by lambda, and then by lambda to the 2, lambda to the 3, lambda to the 4, lambda to the 5, and so on, and they go down. Lambda long, and then the second stage segments are lambda squared long, and then lambda to the 3. Let's again single out these two in the metric space that I have, the original one. So let's say this is xi and this is xj. The fact that they separate at level k, so k depends on your xi and xj, is where they separate. Okay, the first time they separate. It tells us that the distance in the original space of xi and xj is comparable to alpha to minus k, because remember, this horizontal horizontal edges appeared when the balls of that level intersected, and balls at level k have radius tau alpha to minus k, and the tau is a fixed constant, so doesn't depend on k. We can have some estimate of what scale of distance they have in the original metric space. Therefore, if I were to uniformize my graph, the logical choice for what should be the length of these guys so that they add up to something comparable to that would be that you should start with alpha to minus k here, and then alpha to minus k minus 1 here, and so on. So the geometric sum should start with this so that the path distance in the lambda metric becomes comparable to that. So the choice of alpha to minus k is a reasonable way to uniformize a space, my hyperbolic graph. So let's write this. Filling of x with parameters alpha and tau. And then we say choose also epsilon positive, define. So distance epsilon on graph G of x and y, infimum of integral over all path in the graph G e to the minus epsilon d of gamma to the root ds. So gamma is path in G joining x to y, and reminder, such a path definitely exists. Now this looks very different from what I told you, but notice that e to minus epsilon distance gamma s to w0 is e to minus epsilon, and then to the power d gamma s w0. This is your factor lambda. So this is less than 1 because epsilon is positive. This is lambda to that. And if epsilon is log of a, alpha, then it's actually equal to 1 over alpha to the power distance of gamma s to w0. Let's put this note that choice, and then later we see that it's actually an important threshold. Threshold epsilon equal log alpha is a critical and special one. G with this d epsilon is again a metric space, and actually a geodesic metric space. The geodesic part here is that this scaling is locally comparable to just constants, and from that it follows that the new distance is also geodesic metric space. So let's keep that there. So there is a proposition numbered 4.1 in BBS, which says that it actually gives you some definite assumptions. So under certain assumptions, which I don't want to repeat here, under certain assumptions, basically it's the path connectivity of the closure of X on X. If epsilon is strictly bigger than log alpha, then the boundary of G and d epsilon, let's say, so when I say boundary of G, originally we saw that it didn't make sense. It only makes in this new distance, so we put this epsilon to emphasize that, which is by definition the closure of G with this new distance. So you take closure of that, not closure, completion, metric completion of that, minus G itself. So if epsilon is too large, and you have some assumptions on the metric space X, then this guy is a, not is, can be a singleton. One is example of this is if you take 0 to 1/4. We will prove that for epsilon less than or equal to log of alpha, the equality case is very important. The boundary of G is quasisymmetric to the original space X. In the case of epsilon equal to log of alpha, this will be actually by Lipschitz, which will be much better. If you have any questions, please let me know in the comments. Sorry if I go into very long explanations. I just don't want to spit out literature which you can just go on your own and read. I want to really tell my understanding of these theorems, especially through examples, and hope that there will be something worth in doing so. Thank you so much.